So good afternoon, I'm Dr. Richardson, and this course is entitled Using Vector Calculus to Solve Problems in Electricity and Magnetism. So this is lecture 2. Lecture 1 was given a week ago, and it's actually been recorded. So I'm going to review some administrative issues. First key thing is my email address is listed here on this slide. So number of points. If you want to get 100% out of this course, what you should not do is just sit back and watch me. This is not like swimming. You have to jump in and actually do it. So learning is not a passive activity. You should take notes. You shouldn't watch me write on the whiteboard. You need to take notes and go through the arguments as I discuss them. So again, there are problem sets for this course. They won't be graded, but solution keys are available. So as we speak, as of today, June 26th, problem set 1, which was assigned a week ago, has been posted to, it's been here for a week now, to the Google Drive. And the solution key to problem set 1 was posted to Google Drive last night. And the next problem, problem set 2, is also now available on Google Drive. So for students who are registered for the course, you should have access to this information, problem sets and their solutions through Google Drive. Now, when I say do the problem sets, I mean do the problem sets by yourselves. You won't learn anything by working or asking your neighbor or consulting Google or a textbook. Some of the problems are pretty straightforward, some of them are a little challenging, and others you need to think about. But that's okay. And even if you're able to only get through half of a problem or some portion of a problem, that's still great. When you get the problem set solution, then go through that individual problem and just take a piece of paper and cover the solution and just scroll down. So perhaps you can get a hint on how to address the problem. Shouldn't wait till the night before the due date of the problem set. So problem set 2 now is available. Its due date is a week from now. For those who were not able to attend lecture 1 last week, it's been videotaped and it's also available on the Google Drive. And this lecture 2, will be available on Google Drive before midnight tonight. You should ask questions. So the format will be that the lecture will start at 2, end at 3:30, and from 3:30 to 4 will be available online, essentially as a recitation section. That's the time when you can ask questions about problems, problem sets, concepts in the lectures. And in fact, I will extend the recitation time to 5 o'clock. So I'll be available from 3:30 to 5 online, and folks can ask questions. I don't think it's going to work well if 17 or 18 people try to ask questions during the lecture. So I encourage people just to wait to the recitation section, write down on your notes a particular question, and I can always go back to the appropriate slide in my notes. Finally, you're going to need a ruler or some object with a sharp edge, straight edge to it. That will help in drawing a lot of the diagrams and figures that we'll be doing. So again, the central philosophy of this course is really to, both in lecture and in problem sets, get experience in solving problems using the techniques of multivariable calculus, vector analysis, and vector calculus with applications to electricity and magnetism, specifically electrostatics, and if we have some time at the end, magnetostatics. So I'm going to assume that you either attended lecture 1 or have reviewed it online from the video clip, and start with lecture 2. And today I want to talk about coordinate systems. So it turns out coordinate systems are very important because they have unique symmetries. And as we'll see today, those symmetries will allow you to solve certain problems in a much more easier fashion. So the first coordinate system we're going to talk about is the Cartesian coordinate system. And if you looked at the recorded vector lecture 1 video clip, you'll realize I misspelled Cartesian. So my apologies to Rene Descartes. So again, in 3 dimensions, my Cartesian coordinate system can be defined by using my friendly unit vectors. And again, I defined my coordinates using the right-hand rule that we discussed last lecture. So having defined this coordinate system in 3 dimensions, we talked about vectors ad nauseum last lecture. The most important vector in this particular coordinate system is R. And R is the position vector. So you can break it up into its components in the I hat direction, J hat direction, K hat direction. While you're at it, you can also define a very useful creature known as the displacement vector. And in Cartesian coordinates, this is very easy. It's just the derivative of the position vector. So it's I hat times dx plus j hat times dy plus k hat times tz. We will see that this displacement vector, while it is simple to write in Cartesian coordinates, is not necessarily true in other coordinate systems. But more about that later. Okay, so one of the useful things you can ask yourself is, my position vector is no different than any other vector. It has a magnitude and a direction given by a vector r hat. And she has a very special name. We'll call her the radial unit vector. And almost everybody in this part of the galaxy uses that notation, R, for a position vector. So now we're ready, having defined the position vector, in Cartesian coordinates. We're now in a position to actually calculate or write down an expression for the unit vector. It's just the position vector divided by its magnitude. So that's just I hat x plus j hat y plus k hat z divided by the norm of the position vector, which we know is just the square root of the dot product of r with itself. And that just turns out to be x squared plus y squared plus z squared, the entire quantity taken to the 1/2 power. So you need to show that the radial vector dotted into itself gives 1. And that's very easy to show just by using the definition of the radial vector here. So in terms of vectors and unit vectors, that's really it for Cartesian coordinates. And again, the position vector is pretty straightforward to write down. Again, I'll remind you that the displacement vector is also very straightforward to write down. Excuse me. And remember, you don't have to go through lots of gyrations to derive these guys. You will not have that luxury in other coordinate systems. So before we leave Cartesian coordinate systems, we probably should ask an important question. How does one integrate? In Cartesian coordinates? So it's a very important question. So again, we'll go back to this habit of drawing our coordinate system using the right-hand rule. X, Y, Z. And I'll put my unit vectors in here always to let me know what's going on. Unit vectors, of course, have a fixed direction and a magnitude of 1. So what I would like to be able to do is, here's my position vector R. And at this point, there is a little small box, which we'll call dV. And this has a name. We'll call this the differential volume element. And if we are going to do an integration in 3 dimensions, then really what we want to do is figure out how much volume is inside dV and just add up all of these little boxes throughout space. And that'll give us a final volume. That's what integration is. Integration says if you have a region of space, you can find out what the value of that region of space is by just dividing the region of space into little small creatures. In this case, a differential volume element, calculate that, and then add those differential volume elements throughout the entire system. So let's see exactly how to do that. In this case here, the differential volume element is very easy to write down and see what happens. Using my coordinate system, this side of this cube is dx. This side of the cube has to be dy, and this height is dz. So it clearly follows that the differential volume element in Cartesian coordinates is just dx, dy, dz. So in fact, suppose you want to do this integral. So there's some flashing lights. First of all, this v written under the integral sign tells you immediately that this is not an ordinary integral. This is a volume integral. It's an integral over 3 dimensions. So it's a triple integral. Okay. So how do you do that triple integral? Well, you need the differential volume element in Cartesian coordinates, and that's just dx, dy, dz. So you are faced with doing a multiple integral, an integral over 3 different variables, x, y, and z. To first order, that looks scary. It's not, because x has nothing to do with y, which has nothing to do with z. Those are 3 independent variables. And so that means that this triple integral just breaks down into doing 3 separate one-dimensional integrals. So how will we do that? So I'll just rewrite what we had before. So if you're going to evaluate in Cartesian coordinates a volume, you need to know the limits of integration as well as the differential volume element. I've already given you the latter. What about the former? Well, let's assume that we want to just find the volume of a cube. And let's say that cube has a height of A, a width of B, and a length of C. And let's say, for argument's sake, that X goes from 0 to A, Y corresponds from 0 to B, and Z corresponds from 0 to C. As you'll see, the final answer won't matter. Won't depend upon the order of operation for these integrals. I could do the integral over x first, and then do a y, and then do it over z, or I could use dz first, then y, then x. These are all independent variables. So at the end of the day, you get something that makes perfect sense. Then when you evaluate that triple integral, which initially looks like a challenge. It's not. It just breaks down into 3 separate one-dimensional integrals and gives you a volume of A times B times C. So that's really all we want to say for Cartesian coordinates. Next, let's focus on plane polar coordinates. Because you can imagine problems that you want to solve in electrostatics where you could formally solve the problem using Cartesian coordinates, but it's a lot of work. Whereas if you realize that the problem had some symmetry to it, then doing it in plane polar coordinates would make life a lot easier. And that's exactly the motivation for discussing that. Okay, so let's define what we mean by plane polar coordinates. So again, here's my coordinate system. It's in the plane, so it's just 2-dimensional. I need my trusty unit vectors I hat and j hat. And I'm going to define a vector which I'm going to call rho. So that's the Greek symbol for rho. And this vector, you can construct a dotted line that's perpendicular to the x-axis. And you can define an angle, which we'll call phi, that vector makes with the x-axis. So again, using the trusty rule of decomposing a vector into its components, it's easy to see that in fact this length here is just rho cosine of phi, and this side is rho sine of phi. So you really have a right triangle. Now, warning. You will see in other courses and other textbooks and in the literature that instead of using rho in plane polar coordinates, some people use r. And instead of using phi for the angle in plane polar coordinates, some use the angle symbol theta. I'm not going to do that here. And I'm not going to do that for a very particular reason, because it's going to make my life a lot easier when I start talking about cylindrical polar coordinates and spherical polar coordinates. Okay, so let's apply the machinery we talked about last lecture. Rho is a vector, so just treat it like any vector. It can be decomposed into its components. I hat rho cosine phi plus j hat rho sine phi. Again, please remember the trick from last time. Namely, if you don't trust this expression, or you're not sure it's right, or you're not sure you've decomposed your vectors correctly, look at limiting cases. Particularly when phi is 0, you should be able to figure out what rho is. And when phi is pi over 2, you should be able to figure out what rho is, and it should make sense. So for example, if phi were 0, the sign of 0 is 0, there's no contribution in the latter term, but the sign of 0 is 1, so your vector lies entirely in the positive x direction, I hat time with a magnitude of a rho. Okay, as we saw last time, it's important to figure out what the unit vectors are for a particular system. So we're next going to focus on looking at unit vectors in plane polar coordinates. Okay, so just to remind us so we're on the same page. Plane polar coordinates, I have my x-axis, y-axis, my unit vectors. Sorry, that's a little, whoops. It's a little sloppy. So again, I'm going to refer to this vector by the symbol rho, and it's going to make an angle phi with the x-axis. And I said this in lecture 1, phi is a vector. Angles are vectors. We'll come back to this later. You can either go clockwise or counterclockwise. So they have a magnitude, but they also have a direction. So here the direction is counterclockwise. It starts with the x-axis and goes in a counterclockwise direction. So what are the unit vectors in plane pole coordinates? So rho, as we just saw, is this I hat rho cosine phi plus I hat rho sine phi. If I want to find a unit vector, all I have to do is take the vector that corresponds to that unit vector and divide it by its magnitude. So if I do that, I simply get I hat cosine phi plus j hat sine phi. This is extremely important. And again, you don't have to memorize it. You can derive it instantly, because you can say to yourself, oh, I've gotten this right. And the way to see if you've gotten it right is look at limiting cases. We're going to be using this trick throughout the entire course. So you get an expression that's complicated and you want to make sure if it's okay, limiting cases will bail you out. So that's not the only story. I know I have an expression for the unit vector rho hat in plane polar coordinates. So what I need next is a unit vector or expression for the unit vector of phi hat in plane polar coordinates. Okay. And I claim that you can derive that very easily by making sure you know what's going on. So again, diagrams are always going to bail you out. If you're ever lost, write a picture, write a diagram. So again, hence the need for a ruler. So here is my vector rho, and associated with that vector rho is a unit vector. That unit vector points in the same direction as the vector rho, but it has magnitude of 1. Now, I just said that there's an angle phi that you define in a plane polar coordinate system. And I also said that phi, being an angle, is also a vector. So it has a magnitude, but it has a direction. So the unit vector, phi hat, is simply given by this guy. It's the direction that this angle moves at this point. And you can see that the direction of phi hat is not a constant. It's going to be changing. Initially it's going to be upward, perpendicular to the x-axis, and it's going to be changing as you increase phi. So this is extremely important to realize. This unit vector is not a constant. And as you imagine, or might imagine, it's going to depend upon, clearly, the value of phi. And so we need to figure out what that is. So this really boils down to a problem in vector analysis. Namely, I'm going to take this vector in red, which is a unit vector phi hat, and I'm just going to move it to another picture. So it looked exactly like that. Here's the y-axis, here's the x-axis. This angle is theta, is exactly the same as that. Think about that. If in this case, up here, if you let theta go to 0, then phi hat will be pointing straight upward. And that's exactly what will happen here in this case. Now, this guy is a vector. It's a unit vector, and I would like to resolve it into its components. So the question is, how do I do that? And the answer is very carefully. Here is the vector phi hat. And I recognize that what I have here is a right triangle. This is also a right triangle. So points A, B, C, point A, B, C. This is angle phi. This is phi hat. So I can just easily resolve the unit vector phi hat into its components. This first component here is going to be the sine of phi, because after all, the sine of phi is the opposite side over the hypotenuse. In this case, the hypotenuse has a magnitude of 1, because the length of this unit vector phi hat is 1. Similarly, this side has to be the cosine of phi from trigonometry. So now I'm almost there. I'm almost in the position to write down the definition of the unit vector phi hat in plane polar coordinates, but I have to be very careful. The x component has a magnitude of sine phi, but it points in the minus I hat direction. Hence, I need a minus sign here. Fortunately, the component, the z hat component, still points in the positive z hat direction, and trigonometry tells me what it is. Now, again, this is an extremely useful exercise for you to do. I'm not going to do it in lecture. Do you believe this expression? Have you done your analysis correctly? Look at this guy. Ask yourself, does it give you the results you'd expect to see if you let phi equal 0 or phi equal pi over 2? So I have solved my problem. I know what the unit vector phi hat is in plane polar coordinates. So for plane polar coordinates, I have built or discovered that the unit vector rho hat is I hat cosine phi plus I hat sine phi, and the unit vector phi hat, is minus I hat sine phi plus j hat cosine phi. Check these guys. Check in limiting cases. Make sure that if you go back to the original figure we wrote, that you see or you prove to yourself that I hat and phi hat behave the way they should in the limit, in two limits, phi equals 0 or phi equals pi over 2. Extremely important thing to do. While we're at it, you could also write down an expression for the unit vectors I hat and j hat in terms of rho hat and phi hat. I will just tell you what they are. And in fact, I've left this for you to do as an assignment in problem set 1. Okay. So this is problem set 1. While we're at it, why not figure out what the dot product of rho hat is with phi hat in plane polar coordinates and find out what the dot product of I hat with J hat is in plane polar coordinates. Without doing any mathematics, you know that I hat and J hat are orthogonal, so this had better be 0. So if you take the dot product of these two guys, you should see instantly that in fact, that's the case. So again, check your expressions. Just don't believe the expressions that you derive or someone gives you. Okay, so before we leave plane polar coordinates, I think it's useful to go over some nice simple applications that we're going to need later on. So we might as well, my goal is to try to go through all the mathematical techniques we need first, and then we'll worry about applying them later. So applications in plane polar coordinates. Okay, so a couple of things. Let's talk about the circumference of a circle. So suppose you have a circle that has a radius of rho. You know the circumference of this circle from high school mathematics is just 2 pi rho. So is there a way to in fact prove that? Well, there is. What you want to do is ask yourself the following question. Suppose I take that circle and look at, I'm starting over again. Suppose I ask myself, what is the magnitude of this distance ds? So let me pull this out. So there's a wedge that you can pull out from the circle. This quantity d lowercase s is something we'll call the arc length. And if you want to be exact, it's a differential arc length. So I would like to know, what is it? Well, this thing is certainly phi in plane polar coordinates. This side is just rho, and that side is rho. So in fact, I will make the assumption, which I'll prove in a minute, that the right expression for the differential arc length of a circle is rho times the derivative of phi. Now, dimensional analysis is extremely important in science and engineering. So ds clearly is a creature that has units of length. Rho is the radius of my circle. He certainly has units of length. My angle, therefore, has to be unitless, or d phi has to be unitless, and phi is in units of radians. Radians have no units. So I'm almost ready to solve this problem. If I want to find the circumference of a circle, this circle, what I should do is integrate the differential arc length, ds, over the entire circle. Now, this is an example of something called a line integral or a path integral, but it turns out to be extremely easy to solve in this problem. The differential arc length is just rho d phi. Rho, the radius of a circle, is constant. It comes out of the integral. And if you want to integrate over the entire circle, then phi goes from 0 all the way to 2 pi. So in fact, we have stumbled into something that is true. The differential arc length for a circle, ds, where s is a capital S, is simply rho d phi. That's the right creature you want to use. And the reason it's the right creature you want to use is when you actually integrate it over the entire circle, you get what you expect to get. And I suspect that this should be rho. Okay. Actually, let me clean that out just a little bit. In this case, let the circle have a radius of r. So I don't have to confuse the r and the phi. So my final answer here will be 2 pi. R, which is correct. Actually, I talked my way out of something that I don't need to be that particular. This is fine. It could still be rho. So let's not make things more complicated than they need to be. So that's fine. So again, in doing this integral, this line integral, the rho is a constant that just comes out. The integral of d phi over c is just 2 pi rho. Okay, let's look at another example of how to use plane polar coordinates. Suppose you want to calculate the area of a circle. So in fact, here is a circle of radius r. High school mathematics tells me exactly what that area is. It's pi r squared. But I want to try to figure out another way to get this answer, or in fact, to prove this answer. So what I'm going to do is essentially construct something which I'll put in red. And this will be a differential surface element. So it's a differential surface element in plane polar coordinates. And I want to know, what is this guy? Well, let's go back to what we discussed previously. Let's take this picture and blow it up. This is an angle phi. This is rho. This is rho. This length here is just d rho. And this side is an arc length that has a magnitude of rho d phi. And the task at hand is to figure out what the area is of that shaded region in red. Well, geometry just says all I have to do, I mean, these are differentials, so I can sort of get away with it. This thing looks like a square, and the limit that the differentials get smaller and smaller and smaller. I just multiply the length of one side by the length of the other. So ds, the differential surface element for plane polar coordinates, is just rho d rho times d phi. So again, it's important to go back, review this diagram, review what we know about how to calculate an arc length. We did this before. And so this is just an arc length here. It's a differential arc length. But it's just one side of the object that you'll need if you want to calculate the area ds that's shaded in red. You need this side also. Rho is here, d rho is there. Okay, so take a breath, ask yourself, okay, two questions. Is this correct? sorry, yeah, how do I get this? And again, that means reviewing, going over your notes, reviewing this discussion. If you have questions, you can pose them to me. And trying to prove to yourself if you believe this expression. So let's look at the latter first. So again, I claim that the differential surface element in plane polar coordinates is d capital S rho d phi. So if that's true, and I want to calculate the area of my circle, what I do is I take that circle, I divide it into small regions, namely d capital S, differential surface elements, and then I integrate or just add those up over the entire circle. This is a surface integral. It's not an ordinary integral. It's an integral, it has two variables, but it's easy to see what it is. Namely, I have to integrate over phi. Phi is going to go from 0, the center of the circle, to the radius of the circle, which we call r. And theta starts at 0, goes in a counterclockwise direction, and traverses a distance of 2 pi radian. And so that's the integral I have to evaluate. So the purpose of this exercise is to see if this expression makes sense for the differential surface element in plane polar coordinates. You can do this integral just as well as I can. Remember, phi and rho are independent variables. So even though you have a double integral, it really reduces to doing two separate integrals. And you should convince yourself that this is simply 2 pi over 2 r squared, or it's pi r squared, which is the radius, which is the area of a circle. Okay, there is another useful way, and we might as well discuss it now because we're definitely going to use it later, to integrate over a circle to get its area. So what is that? So here's a circle. Let's say the circle has a radius of r. And what I'm going to do is divide this circle into annular rings well, let's just say we'll do this one at a time, into an annular ring, so one of them, of radius rho and width d rho. So what am I talking about? So in red is my annular ring. It has a radius of rho and a width of d rho. So the question is, what is this area, this shaded region? So let me say how I'm going to solve the problem first, and then I'll do it. What I first want to do is ask myself, what is the region of space ds? And again, here in plane pole coordinates is phi. What is this guy ds? Well, we did that last time. The differential surface element is just rho, d phi. Next, I want to do is add these contributions up and go around the entire circle so I can get an expression for the differential surface area of the annular ring. So to do that, what I simply have to do is take this small little region ds and integrate over the angle phi. If I do exactly what I just said I'm going to do, I find that the differential, the area of my annular ring is just 2 pi rho d rho. Okay. So what's shaded is 2 pi rho d rho. What's here is rho d phi. And I used my knowledge of the differential surface element in plane polar coordinates to calculate the area of this annular ring, this shaded red region. Now, I'm not finished. I mean, I wanted to find what the area of this circle is. Well, the idea is if I know what the area of this circular annular ring is, and I just add all these guys up from 0 all the way out to the radius of the circle r, I will get the total area of the circle radius r. So in fact, let's see if that's exactly true. So if I take this guy, which I know now is 2 pi rho d rho, and the only variable is rho here, so it starts from the 0, the center of the circle, and goes out to the radius of the circle, then you can do this integral just as well as I can, and you'll get pi r squared, the area of the circle. So these are 3 different ways to come up with the same answer, but it's important to see now how, in fact, you use these techniques, how you do this. And again, learning is not a passive activity. You write the notes as I discuss them in lecture. You go home and review the notes. If you have questions on the notes, you shoot me an email message. Again, for questions, I'm available by email anytime during the week or the weekend, and I promise I'll respond to you in writing within 24 hours of your email message. Okay, so for the moment, that's everything we want to do. With our discussion of plane polar coordinates. And I said this before, I'll repeat it. We use rho, some authors use r, we use phi, some authors use theta. So we will use this. And I just mention this because you will see this in other textbooks. And then you could ask the reasonable question, well, why are we choosing this scheme and not this scheme? And the answer we will see next when we start talking about our next coordinate system. Cylindrical polar coordinates. So the logic is to start with plane polar coordinates then go to cylindrical polar coordinates, and then ultimately spherical polar coordinates. Okay, so let's jump right in here. There are going to be problems that have cylindrical symmetry, hence the term cylindrical polar coordinates. So I need to define what I mean by cylindrical polar coordinates. So I'll start out again. I'll draw my coordinate system. And there's some point in space given by a vector. And I don't want to express this in Cartesian coordinates. I want to express this in polar coordinates. So what am I doing? So first things first, I'm going to draw a perpendicular line from that point down to the XY plane. In the XY plane, there's going to be a distance from the origin to that point. And now I'm going to use everything I just discovered about plane polar coordinates. I'm going to call this vector rho. And I'm going to call this vector phi. So the XY plane is just another illustration of plane polar coordinates. The final thing I have to give you to uniquely determine this point is I need to know its distance with respect to the x-axis, and that's just the variable, oh sorry, z-axis, and that's just the variable z. So the important coordinates for cylindrical polar coordinates are rho, phi, and z. And there they are. And I said this last time, z I put with a horizontal bar through because I don't want to confuse that with the number 2. And again, that's a right triangle, and that's a right triangle. So the next question I'd like to ask is, like I asked before, what are the unit vectors in cylindrical polar coordinates? Now you'll see why I went to the trouble of using this notation of rho and phi. So here's a point in space. I could define it by x, y, z. Those are Cartesian coordinates. I'm choosing not to. I want to define it in terms of these 3 new coordinates, rho, phi, z, because they'll have something to do with helping me to calculate problems or to work with problems that have cylindrical symmetry. Okay, where in a sense, rho is just the radius of the cylinder, z is just the height of the cylinder, and phi is just an angle that tells you where you're going around. Phi has another name. It's called the azimuthal angle. And in a sense, that's all I need. By just writing this diagram, that's all I need if I'm going to understand what's going on in cylindrical polar coordinates. Those are the most convenient, the 3 most convenient variables to use. So let's ask this question, let's answer it. What are the unit vectors in cylindrical polar coordinates? So what are we talking about? Well, there's a rho hat, there's a phi hat, and there's also a z hat. I can write down the unit vectors for rho hat instantly. I did this. I did this for the case for plane polar coordinates. They're just this. And again, if you don't believe this expression, look at the limiting cases and make sure you agree with what the figure is telling you. And the limit that phi is either 0 or pi over 2. So that's easy. Phi hat is also easy. I did it. I set it up before. Remember that minus sign, where it came from when we looked at plane polar coordinates. So again, check this guy. Make sure you believe it by looking at limiting cases. So really, the unit vectors for Cartesian cylindrical polar coordinates are very easy to write down. So I'm missing one person. And actually, I will use, to be consistent with my notation from lecture 1, this will be k hat. So k hat is just k hat. That's it. The unit vectors for cylindrical polar coordinates are just the same as the unit vectors for plane polar coordinates plus this additional k hat vector. Okay. There's my x, y, z. Here are my unit vectors I hat, j hat. But I don't need to talk about x, y, and z anymore. I can just express this problem in terms of phi, essentially, and my unit vectors. Okay, I leave for you as an exercise. You did this in plane polar coordinates. Do it also for cylindrical polar coordinates. Figure out what these dot products are. Actually, before you even do the calculation, figure out what the answer is, and then do the calculation and see if your calculation is correct. So you're given these 3 expressions for the 3 unit vectors in cylindrical polar coordinates. And I actually ask you in problem set 2 to show, I'm sorry, problem set 1, I actually ask you to show that you can use those 3 definitions to write down the unit vectors I hat, k hat, and j hat in terms of the unit vectors for cylindrical polar coordinates. I'll tell you what the answer is, but you need to do the assigned problem in problem set 1 and prove to yourself that it's true. There's I hat. There is the first component of j hat. Note there's a minus sign here. There's no minus sign there. And there's k hat. Same story. Go back and look at limiting cases to see if these expressions are correct. For example, instead of having rho hat, instead of saying that j hat is rho hat sine phi plus phi hat cosine phi, suppose I wrote sine phi here. Well, if I look at the limiting case where phi is 0 or pi over 2, that'll show me whether or not I get something that makes sense. It won't, and so that means I've made a mistake. Again, you know that I hat dotted into j hat is the same as k hat dotted into I hat, which is the same as j hat dotted into k hat, dot, 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 when all these guys are 0, because unit vectors I hat, j hat are orthogonal to each other. You should prove that explicitly for this case of the unit vectors for cylindrical polar coordinates. Finally, before we leave our discussion of unit vectors for cylindrical polar coordinates, let's go back and look at the position vector. I'll do that on another slide. So, position vector in plane in cylindrical polar coordinates and again, the reason why I wanted to pick another, use this on a fresh slide is I want to remind ourselves what the coordinate system is. So again, my unit vectors tell me something about the orientation. I hat, j hat, k hat using the right-hand rule. In cylindrical polar coordinates, if you want to specify the coordinates of that point, you drop a line that's perpendicular to the xy plane. You can then draw a line from the origin to that point. So this is a right triangle. This is simply the angle or the length rho, and that's simply the magnitude of the vector phi, the azimuthal angle. And let's do this a little bit more carefully. This distance here is simply z. So rho, phi, z. Those are the three independent variables in cylindrical polar coordinates. The position vector, r, is just going to be the vector rho added to the vector z. Okay. This guy added to that guy. That will give you the position vector rho, r. What is that? It's easy to write down. I know what these guys are. I did this work before. It's just I hat rho cosine phi plus j hat rho sine phi. That I learned from my discussion of plane polar coordinates. And then I just need an I hat, a k hat, times z. Again, prove to yourself that you know what the unit vector r hat dotted into r hat is in cylindrical polar coordinates. Prove to yourself that you know what r hat is dotted into itself in cylindrical polar coordinates, and calculate the norm, length or magnitude of a vector in cylindrical polar coordinates. You can do all this with that and that. Okay, so let's look at some applications. So applications. For using cylindrical polar coordinates. So I'm going to need some artistic skills at this point. Okay, let me draw my diagram. My coordinate system. And again, I'm calling the cylindrical polar coordinates for a reason. Where's the cylinder? Well, here it is. We can pretty this up a little bit. Okay, so the artwork is over. There's the x-axis, the y-axis, and the z-axis. Again, let me put in my unit vectors in employing the right-hand rule. So a vector from here to this point is clearly rho. This height here is clearly z, and this angle is clearly phi. And now you can see why those three variables, rho, phi, and z, are the natural set of variables you will need to describe a cylinder, hence the name cylindrical polar coordinates. So the next thing I want to do is ask myself, what is the differential volume element? dV for cylindrical polar coordinates. I know what it is in Cartesian coordinates. It's just dx, dy, dz. I know what the differential surface element is for plane polar coordinates. That's two-dimensional. And cylindrical polar coordinates are three-dimensional. So I need to be able to figure out what the volume of that cube is. And so let me blow it up for you. And you may say, well, that's not precisely a cube, right? Well, it is in the limit when you let those sides get smaller and smaller. Hence, that's why you use differential volume elements. So if I knew what the length of each of these sides were and just multiplied them, that would give me dV. So what are these folks? Well, if you look at the diagram, let me pick the easy one first. This height, and again, here in my coordinate systems, here in my unit vectors, so that tells me what's going on. This side is simply dz. That's easy. This side is a little less complicated. It's just d phi. This guy, I actually know what it is from my discussion of plane polar coordinates. Well, let me rephrase that. You should be able to prove to yourself that you know what it is. It is nothing more than rho d phi. So I'm in business. The differential volume element in cylindrical polar coordinates is just rho d phi, rho d phi dz. That's what I get when I multiply all three of those things together. Now, is this a volume? Well, rho is a length, d rho is a length times a length is an area, phi is an angle, she is dimensionless, having units of radians, dz is just a length. So this quantity on the right-hand side is clearly a length times a length times a length, so it's a volume. So at least dimensionally, this guy makes sense. The question is, can you prove it to yourself? Can you prove that, in fact, this expression is actually true? Well, two steps, same story. You need to go through this derivation to convince yourself that, in fact, the analysis that we went through is correct. And the next question is, if this is correct, then it should give us the correct answer when we start applying it to problems. So what am I talking about? Suppose I ask myself the following question: what is the volume of a cylinder? So, what's a cylinder? Cylinder is a creature that looks like that. Typically has a radius, which we'll call r. And in this case, it has a height, which we'll call h. And we'll let the bottom the XY plane be h equals 0. Again, this is a so-called right cylinder because it's aligned in the positive z direction, positive z direction. Let me get my unit vectors right. So what am I trying to do? I want to calculate the volume of this cylinder. The way I do this is I just break the cylinder up into little differential volume elements, dV. I know what those guys are. They're rho, d rho, d phi, dz. And I do this integral in 3 dimensions. It's a volume integral. So it has 3 integrals over which you have to integrate. These variables, rho, phi, and z, are independent of each other, so the order of integration is irrelevant. Rho goes from 0 to r, phi goes from 0 to 2 pi, and z goes from 0 to h. So the whole point of this is to try to prove to ourselves that this guess, not guess, we actually derived it, but this expression for the differential volume element in cylindrical polar coordinates is correct. I leave this integral up to you to do. You just break this down into 3 separate integrals, and you'll find, lo and behold, you'll get the answer of pi r h, which is in fact is the area of a cylinder. Area of a cylinder is simply the area of one end multiplied times the height of the cylinder. The cylinder has a radius of r. So this expression is good. This expression is correct. I want to use this expression now for a more complicated example, which we're going to exploit later on. So another useful way to integrate actually, it turns out I will not. I'll leave that for a future discussion. Okay, so where are we? Well, we've looked at Cartesian coordinates. We've looked at plane polar coordinates. We've looked at cylindrical polar coordinates. And we'll leave the best to last. There are problems that have spherical symmetry. And these problems would be really hard to deal with if you use cylindrical polar coordinates or Cartesian coordinates. So this is what we want to focus on next. So we started this lecture late, so I'm going to 4. And then we'll do the recitation at 4. Okay. So spherical polar coordinates. So this obviously has something to do with spheres. So always go back to the beginning. I need to tell my audience what's going on here. So here's my X, Y, and Z axes. Here are my unit vectors, I hat, J hat, K hat. So let me have a trusty position vector, R. let me in fact take the point, the head of that vector and drop a line that's perpendicular down to the XY plane. Again, I'm going to use all the notation I set up in my discussion of plane polar coordinates and cylindrical polar coordinates. That distance will be rho. This will be the angle phi. And I'm going to draw a line that's parallel to rho. And I will define a new angle, which I'll call theta. So theta has a name. It's called a polar angle. Phi, we saw before, also has a name. She used it as a azimuthal angle. And warning, there are people who write textbooks and papers and research projects where these two are interchanged. Some people call phi the polar angle, some people call theta the azimuthal angle. We will not. Okay, so what's the task at hand? The task is to realize now that my position vector rho depends upon three coordinates. My position vector r depends upon three coordinates: rho, theta, and phi. Okay, so let's start from the beginning. First question you want to ask is, what is the position vector? R in spherical polar coordinates. So let's go back to that diagram. And it's easy to see what that answer must be. This is X, Y, Z. Again, you always need to draw figures or pictures. They're going to help you solve a problem, any problem for that matter. So that distance is rho. This distance is Z. Here's my position vector R. In fact, if you want to be formal about it, those are vectors. So I immediately know what the position vector is. It's just the vector rho added to the vector Z. I know what the position vector is from my discussion of plane polar coordinates. That's just I hat rho cosine of phi plus j hat rho sine of phi. And then I have Z, the vector Z, and that's just j k hat times the distance Z. So I'm almost there. I need to get an expression for a position vector, but I need to figure out what is rho. So if I look at this diagram, where again, this angle is theta, I can pull out of this diagram a nice little right triangle. That nice little right triangle is going to have a side Z, a hypotenuse of R. This angle is theta, and that distance is R. And now I'm in a position to write down an exact expression for the position vector R in spherical polar coordinates. Note from this figure, the sine of theta is rho over R. So let's write that down. The cosine of theta is Z over R. So I have an expression for my position vector in terms of rho and phi. I want an expression for my position vector in spherical polar coordinates for just theta, phi, and r. And here's the secret. Here is the functional dependence of rho on r and theta. So all I need to do, this is lecture 2, is take expression 2-1 and substitute into it expression 2-2. So the position vector in spherical polar coordinates is just going to be I hat r sine theta cosine phi plus j hat r sine theta sine phi plus I hat z. But remember z, which is r cosine theta. Okay. Now, you should prove to yourself lots of things. You should evaluate what r dotted into itself is. You should look at limiting cases where theta or phi are 0 or pi over 2 or 2 pi for that matter to make sure that you believe this complicated expression. You can read out from this exact definitions for x, y, and z. They are r sine theta cosine phi, r sine theta sine phi, and r cosine theta. And it's a nice, quick, easy way to see that, in fact, what you've written makes sense. Suppose you take the square of x, add it to the square of y, and add it to the square of z. Well, trigonometry will help you. You should do that explicitly, and you will get r squared. So the way to remember what's going on is x has a component. All these guys have components of r. These angles are dimensionless. Sine, cosine. Sine becomes for cosine. So theta, phi. Then it's a sine, theta, phi. And then go back and look at the original diagram. This thing can't be phi. It is theta, okay? Because z and r are related by the angle theta. So in terms of spherical polar coordinates, the position vectors are given as such, or the position vector is defined as such, and the components, x, y, and z, have these definitions. So again, you need to go back to the diagram and prove to yourself that you believe these things. And again, once you've written it down, go look at limiting cases to see, in fact, these expressions are correct. What happens if theta is 0 and phi is pi over 2? Do these expressions give you the right values for x, y, and z? That's an important exercise to go through. So, like we did before for plane polar coordinates and cylindrical polar coordinates, we need to determine the unit vectors for spherical polar coordinates. So this is pretty straightforward. R hat is just r divided by its magnitude. We already derived what the position vector r was. So the unit vector r hat is just a sine I hat cosine of theta cosine phi plus j hat sine of theta sine of phi plus k hat cosine of phi. How about phi hat? What is that unit vector in spherical polar coordinates? Well, we did this. Why reinvent the wheel? We did this already for plane polar coordinates. it is nothing more than minus I hat sine phi plus j hat cosine phi. And again, prove these things for yourself. Test them. Look at the dot product of r hat with theta hat. Look at the cross product of r hat with theta hat. Look at the cross product of theta hat with r hat. Calculate these guys. See if they give you the right results in limiting cases. So we are missing somebody. We are missing expression for the unit vector for the polar angle. So we don't know what this is. So that's the remaining thing to determine. So go back to the beginning. Write down your coordinate system. Again, x-axis, y-axis, z-axis. I can put my position vector in here, but I won't label it just to not make things too complicated. These perpendicular lines define a right triangle. And again, that line here is perpendicular, is parallel rather to that line. So what am I trying to do? Well, my polar angle, theta, is an angle, and I said earlier in the lecture, angles are vectors. So this vector has a magnitude, but it also has a direction. And the direction is defined by the unit vector theta hat. So this is something I want to figure out. I want to know what this is. So if we take this diagram, drill down from it, and just draw another diagram, you can sort of see what's going on. Here's rho. So this distance is designated by the vector rho hat. This distance here is z hat. And my vector phi hat has to look like that. Points down that way. So clearly, I'll call this a vector for the moment. Theta, the vector theta, is just rho hat, or rho, the vector rho minus the vector z, because I'm going downward. I'm going the minus z direction. So what's theta? Theta is rho times rho hat minus z times k hat. I know what rho hat is. I did that previously. So I can break this expression down into I hat cosine phi plus j hat sine phi. And then I have a minus z k hat. And again, this is still a vector. This is not a unit vector yet. But to get a unit vector, all I have to do is get an expression for the vector and divide it by its magnitude. So what's missing here? Well, this term is okay. This term and this term have problems because I don't really know what rho is in terms of the other variables in the problem. If I could figure out what rho is, then I'd have an expression for the vector theta hat divided by its magnitude, and then I'd get a unit vector, the unit vector theta hat. So let's do exactly that. So what is rho? So again, go back and look at my diagram. You're not going to get the answer from the atmosphere of Neptune. The answer is in front of you in the diagram. The diagram tells you what's going on. So here is my vector theta. This is the angle theta. And I can use this time-worn trick of creating a right triangle and using trigonometry. Namely, the cosine of theta is just the magnitude of rho divided by the magnitude of theta. And the sine of theta is just z divided by theta. So I'm set. Theta is now I hat cosine phi plus j hat sine of phi times rho, but I know what rho is. It's cosine of the magnitudes of these guys. They're unit vectors, so the magnitude is just 1. So I'm just left here with the cosine of theta. And I have my final term, which is minus sine theta k hat. And in the last slide, I'll just summarize all this. So what we have found is that our hat is I hat sine theta cosine phi plus j hat sine theta sine phi plus k hat cosine phi. We have found an expression for, let's do the easier one, phi hat. He is I hat sine phi plus j hat cosine phi. And what we just discovered, we've written an expression for theta, the vector theta. If you divide through by the magnitude, you'll get the unit vector. So that's just I hat cosine theta cosine phi j hat cosine theta sine phi minus sine theta j hat. So that's a lot, but there are 2 exercises I'll leave for you to do. Check limiting cases. See if these guys make sense. Suppose theta is 0 and suppose phi is pi over 2. Do you get the right expressions for these unit vectors? Mix these things up. Also, calculate dot products. You know how to calculate a dot product, so do it. Calculate dot products and see if you get the expected answers. Calculate the magnitudes of these vectors. You have to play with these guys. The only way, just sit down and look at them and say, oh, you're not going to sit down and write this by memory, okay? And you'll be given this if you need to do it for an application, but you should at least be able to take the expression and work backwards and figure out that, gee, this expression, even though it's complicated, it makes sense. It jives with something we already know. I want to say one more thing about spherical polar coordinates, and then I need to say something about integration. In problem set 1, I ask you to write down an expression or derive the unit vectors I hat, j hat, k hat in spherical polar coordinates. It's a useful exercise to go through. I'll tell you what they are. So that's I hat. J hat is sine theta sine phi. R hat plus cosine theta sine phi theta hat plus cosine phi phi hat. And K hat is cosine theta R hat minus sine theta theta hat. And so you need to check this from problem set 1. Okay, it's just some algebra, but it's pretty straightforward. All right, an extremely useful application for spherical polar coordinates involves the determination of the differential volume element in spherical polar coordinates. Now, I'm not going to draw a picture of it, but if you look at problem set 1 in the Google Drive, there's a beautiful, simple illustration of it from a book by Donna McQuarrie and Barry Simon. So in fact, the differential volume element in spherical polar coordinates is r squared dr sine theta d theta d phi. Now, I don't know if you need to go out and get a t-shirt, print it up, and go around wearing that, but I will tell you this. You should certainly look at the problem set to see the geometrical derivation of this. But this expression is critical to understand and remember. So you need to get used to using this. You need to know this, just like you know the Pythagorean theorem, or that 1 plus tangent squared of an angle equals secant squared of an angle. Why? Well, a very simple application is, suppose you want to calculate the volume of a sphere. If you want to do that, you'll need to do a triple integral. The differential volume element is r squared dr sine theta d theta d phi. You'll integrate r from 0 to the radius of the sphere. You'll integrate the polar angle theta from 0 to pi, not 2 pi, but pi. Go back and look at the original figure. And the azimuthal angle has to go from 0 to 2 pi. So this integral, which is a triple integral, which looks horrendously complicated, it's not x, r, theta, and phi are independent variables. You can do these integrals separately. You need to do that, and you should convince yourself that you get the answer of 4/3 pi r cubed. And I bring this up because this is a very useful exercise that'll help you remember the right expression for the differential volume element. For example, if you thought the differential volume element in spherical polar coordinates was r dr sine theta d phi, you would not get the answer that you knew from your years in high school. So there's a 2 there missing. Okay, so I'm going to wrap up in about 5 minutes. This is not meant to be a course in calculus, but you need to know what you need to know from your calculus courses regarding integration. And turns out there are lots of ways, well, there are really 4 important ways to integrate something analytically. We're not going to talk about numerical integrals in this course. One is integration by substitution. So for example, the integrand of 1 over the square root of x, where x is not 0. You can do this integral by substitution. You let u equals x. du is just dx. The square root of x is the square root of u, which is u to the 1/2 power. And so this integral you can do a change in variables, and this will get you 2 times u to the 1/2 power plus some constant of integration. Problem set 2, which is available now in Google Drive, gives you lots of practice exercises in integrating and evaluating integrals, in particular using one technique, integration by substitution. That's not the only technique that's useful. So you may have taken calculus, some time ago, but there really are 4 techniques that are time honored that you really have to master. Integration by parts. You want to integrate an integral of that form, it has an answer that looks like this. The integral of u dv is uv minus the integral of v du. So for example, the integral of sine theta cosine theta is an integral that's hard to do by substitution, but it's easy to do by integration. Namely, you will let u equal sine theta, du will be equal to cosine theta d theta. So a change of variables tells you that this integral can be written as u du. You can do that integral easily as an elementary integral, and hence your answer is just 1/2 sine squared of theta. I'm writing these as indefinite integrals, so I'm not worried about the limits of integration for the moment. Third technique for doing integrals, trigonometric substitution. And again, all these methods you're going to have practice with in problem set 2, because when we start to do applications in electrostatics, that's not the time to remember if you can do these integrals. You want to get all these techniques out now. So for example, this integral appears a lot in problems that we're going to solve. So what we'll do is remember that x equals the sine of theta, and that's a useful change in variables that we will exploit. Dx is just going to be the cosine of theta d theta. That means that 1 minus x squared is simply 1 minus the sine of theta squared, and that's simply just the cosine squared of theta. So 1 minus x squared to the 1/2 power is just going to be the cosine of theta. So if you make this substitution, these substitutions, you will find out that the cosine in the numerator will be canceled by a cosine in the denominator, and you just have to integrate over d theta, and theta is just going to be the inverse sine of x. This is an important technique, and you have practice cases for it in problem set 2. Last point, I'm not going to go through an example of it. There is something called the method of partial fractions. And you will need that to evaluate lots of integrals in this course. So I want to finish the lecture in the next minute, and I will just simply say, Google this, or use Khan Academy to see what the method is and how it works. Or if you haven't sold for money your elementary calculus book, go consult that. So the method of partial fractions, for example, will be a wonderful method that allow you to evaluate integrals like that. And it turns out that that solution is simply that, once you use the method of partial fractions. Okay, so we started late. We're supposed to start at 2 o'clock. We started late. I've finished now. We started really about 2:15, 2:20. That's it for the day's lecture. 2 things. I'll be online now for at least the next hour. If people have questions or comments on the problem sets or the lectures, this is the time to speak up. Problem set 1 is available online for people to review and do. The solution key to problem set 1 is online, and problem set 2 is now available. You're in a position to do half of problem set 2 because that involves practice with integration. Next lecture, we'll start talking about line integrals, surface integrals, and volume integrals. Half of problem set 2 involves line integrals. You obviously can't do those problems now. That'll have to wait till next time. Okay, questions or comments? Hello? Okay.
Would you be able to go over some of the problem sets?
Sure. Problem set 1?
Yes.
Sure. So let me get it. So new board, new day. Okay, shoot, go ahead.
Okay, so for problem set 2.
Yes. Problem set 1 or problem 2?
Oh, well, problem set 1 is from problem set 1, problem 2.
Got you, right. So you want to prove, I'll do this for everybody, so I'll write the whole problem out. Prove that the line from the apex of an isosceles triangle that bisects its base is perpendicular to the base. So one of the things I did was, and again, it always helps to start out with a picture first. So you know what you're doing. That's not a pretty triangle. Let's do a little better job. Okay, so there's an isosceles triangle where this side and this side are equal. Let's call this V, and let's call this, or sorry, let's call this U to be consistent. And let's call this, oh, I had it the other way around, sorry. So let's call this V, and let's call this U. And I also said that this vector was defined in that direction, and this vector was defined in that direction. So if you use the parallelogram law of addition, the vector, the base is just U minus V. So apex is the top. And even though it looks true geometrically, you want to show that this line, in fact, not only is perpendicular to the base, but it bisects the base. So in other words, this distance here is the same as that distance. Okay, so one way to do this is to just use vectors. I called this guy M. So what is U? Well, U, if I use the parallelogram law of addition for vectors, is just M plus 1/2 of U minus V. What's V? V is M minus 1/2 of U minus V. So again, I can add these two expressions together. U plus V will simply be equal to 2 times m. And this says exactly what I want to show, that namely m definitely lands in a way that it bisects u, and it bisects its base. Is equal to 1/2 times u plus v. So in a sense, u minus v has to be perpendicular to m. You should show that that's true. But the key thing is that this distance m, this vector m, is 1/2 of u plus v. So I started out with this figure. You need this figure as sort of a hint of how to go. I mean, you might expect that 1 equals 1, but this rigorously shows that. Now, you're still not finished, so I need to go to the next page. And let me write down exactly what I just said. M is 1/2 times u plus v. So the question is, the base of my isosceles triangle is represented by u minus v. So if I take the dot product of m with the base, that's just u plus v over 2 dotted into u minus v. I can do the dot product easily. It's u dotted into u plus v dotted into minus v plus v dotted into u minus u dotted into v. And your answer should simply be the norm of u squared minus the norm of v squared. So finally, our triangle is an isosceles triangle. And I should say, this is not the only way to do this problem. This is just a way to do this. So a lot of problems have many ways to solve. So since this problem is an triangle, is an isosceles triangle, I already see a typo in the answer key. The norm of u squared should be equal to the norm of v squared. So that's what's missing. Well, since that's true, this right-hand side is 0, and m has to be perpendicular to the base. So m is perpendicular to the base of the triangle. And in fact, it has half the distance of u plus v. So perhaps what you were referring to is that there is a missing typo in the problem set solution. That definitely has to be a 2 there. Is that okay?
Yes.
Okay. So apologies for this. Again, this is not the only way to do this problem, but I tried to set it up so it would give you practice in taking dot products of vectors and in calculating norms of vectors. Okay, other questions, other comments? So everything else in problem set 1 is easy?
I've finished up till problem 3.
Okay.
And I was wondering, well, I didn't finish problem 3 to begin with, but
Okay.
I knew that somewhere along the lines, to get that angle phi, I would just have to find the dot product between u and v, correct?
Correct.
And then, hold up, I'm sorry, let me go back to see what I was doing.
So problem 3. So again, even though you have the solution key available, my recommendation is don't look at the solution key.
Correct.
Try the, or you know, look at the solution key and cover it up and then just pull it down and look at it by pieces.
Okay.
So the very first thing that I think you need to know to start doing problem 3 and problem set 1 is you need to be able to take the dot product of 2 vectors,
Correct.
u and v. That's correct. So you need to know what that is. Then you need to be able to know how do you calculate explicitly the angle between any 2 vectors. Okay.
Well, right. I believe there's a formula for once you find a dot product of 2 vector, you equal that to, I think it's the magnitude of the 2 vector times cos of theta.
Well, that's a formula, but that's something that you should not have to, you should know that.
Okay, right.
So in fact, new page. So I'll start you out. So if you have a vector A, sorry, don't like red. So if you have a vector A and you dot it into a vector B, this is a definition. This equals the norm of A times the norm of B times the cosine of the angle between them.
Right. Okay.
Angle between A and B. And A and B have to be placed so that they are tail to tail.
Ah, okay.
So that's A and that's B, and here's an angle theta. Okay. So that's how you define, we did this in lecture 1, that's how you define the dot product or scalar product with 2 vectors.
Right, right.
So, sorry. So this expression can be used to solve for the cosine of theta. Excuse me, it's just the dot product of A with B divided by the magnitude of A times the magnitude of B.
Okay.
So clearly this expression doesn't get you into trouble because A and B are not 0. If A and B were 0, their magnitudes would be 0 and you'd have an expression that diverges, right? It has a denominator that goes to 0. And that's not the case. The other thing, I'll give you some more clues. The other thing you want to recognize is that theta, pi in this problem, I'll call it pi. It is pi if you look at the diagram.
Right.
It's theta plus
Theta plus phi is 1/8.
Right. So that's how those guys are related. I'll give you one other hint. You will probably need, I'll do this on the same page. If this vector is u and this vector is w and they're written tail to tail, then this vector here using the parallelogram law of addition has to be w minus u. And we'll call that vector v. Because if you add the vector u to the vector w minus u, you get, well, this is probably just, so that's defined in the diagram. So that's another way. If you don't want to carry the w minus u around, you can just replace it by v.
Okay.
So I would say hint number 1 is that. Hint number 2 is that. Hint number 3 is that. And hint number 4 is that.
Right, okay.
Now, I'll say another thing. You don't have to do the problems linearly. You can jump around. I mean, they're not written, I mean, they're written in the order of the material that's covered in lecture. But if you find a particular problem challenging, then skip it. Come back to it.
Right.
Because, for example, I think, this is just me, I could be wrong, but I think problems 4, 5, and 6 are easier than problem 3.
Right.
And definitely problems 7, 8 are easy. Well, yeah, a little easier. Problem 10 is really a beast. And problem 11 is a beast, is definitely the beast. And 12 and 13 and 14 are. But I would say just to get some practice, get some confidence under your wings, try 4, 5, 6, and 7 and 8 first.
Okay.
and you can always come back to it.
Right.
So what's the purpose of the problem set? The purpose of the problem set is so that you're familiar with the idea of taking a dot product of two vectors.
And
You're
the cross
familiar with the
product.
idea of what the norm of a vector is.
Mhm.
You're familiar with how to calculate the angle between two vectors. You're
Mhm.
familiar with the fact that when two vectors have a dot product at 0, that means that the vectors are parallel, orthogonal, or perpendicular to each other. You're familiar with cross products, what it is. You're familiar with a lot of vector activity identities involving the cross product.
Mhm.
And then you're familiar with unit vectors, both in plane polar coordinates and spherical polar coordinates. And we actually talked about those today.
Mhm.
So this is a fundamentally important problem set. You shouldn't even look at problem set 2 until you have mastered this, because these are all things that you need to know. The idea is to build on foundations and fundamentals and then go forth.
Okay.
So I agree with you. 3 is a little challenging. There's some geometry there. There's some
Right. Right.
trigonometry there. Whereas 4, 5, 6, 7, 8, and 9 are algebra.
Mhm.
Okay. And I don't know about you, but in high school, I did better in geometry than algebra because I knew how to draw pictures. Algebra was, a little more challenging.
I
So,
actually, I've never had a formal geometry class. So
okay.
everything I know from geometry, I just picked up in like trigonometry or
Okay.
throughout like calculus or something like that.
Okay. Okay.
Or pre-calc for the most part.
Okay.
So yeah,
Are you familiar with Khan Academy?
yeah, I've used it sometimes.
Okay. So I mean, I like Khan because if you're stuck on what is the law of science and you just
Mhm.
Google Khan and law of science, he'll come up with a nice 5-minute discussion of it.
Mhm.
Or if you're lost with, or you need practice with, I don't know, adding vectors, he'll do that. And again, the way to do this or any course in STEM is just practice. You have to keep practicing problems. The more problems you do, the better you will be at.
Mhm.
So I definitely want everybody to make sure that even though you've got problem set 1 in hand, go through the entire problem set before you look at the solution key. But thank you for pointing out the typo in problem, what did we say? It was
Sorry. Problem two.
problem 2 and problem set 1, yeah.
Okay. All
And
right.
if you remind me, and I can make that comment again next time.
Okay. Well, I'm gonna try to figure out the rest of the problems before I move on to problem set 2.
That would be advisable.
Right. So then I feel like problem set 4 through 7 should be a little more straightforward, as you mentioned that it's just algebra.
It's just algebra. That's right. That's
Um,
exactly right.
right.
But it's useful algebra. So it's algebra. Yeah. I
Okay.
think problems 10, 11, 12, 13, or 14 are algebra too,
Mm-hmm.
but they're a little bit more sophisticated than 4, 5, 6, 7, 8. And
Mm-hmm.
again, if you get stuck, I mean, there are 2 ways to do this. If you get stuck on a problem, you can go look at the solution key, cover it up, and just look at it line by line. Or you can shoot me an email about a question, and if you need a hint, I can give it to
Okay, perfect.
you. Okay.
Okay. I
All
think
right.
that's about it. All righty. Thank you,
Th-
Dr. Richardson.
thank you.
All right,
Other que-
guys.
I'm sorry.
No, I don't have any other questions for now, but I'm pretty
Okay.
sure once I start getting into deriving the unit vectors and stuff like that for like the polar coordinates and other coordinate system, I'll have more questions moving
Okay.
forward. Yeah.
Were you able to attend lecture 1 last week?
Yeah, I was.
Okay. So we put the video clip of that lecture, and that may or may not be helpful also. But if you attended the lecture, then that's fine.
Yep.
But again, start. I agree with your strategy. Don't even look at problem set 2 until you get problem set 1 finished.
Right, right. Okay.
Okay. All right. And then for that matter, just a suggestion. I mean, I wouldn't even go back and look at my notes and review problem set lecture 2 yet until you got problem 1 out of the way, problem set 1 out of the way.
Right.
Then the video for this lecture will be available online in Google Drive before midnight tonight.
Okay. That's
Okay.
fine.
All right.
All
Thank
right.
you.
Dr. Richardson. All
Thank
righty.
you.
Bye.
Bye. Other questions or comments? Hello, who's out there in cyberspace?
I'm here. I don't know. I think that's it. I think everyone else is off.
Well, you can tell from your end because you can look at the, so it's just the two of us?
Yeah, let me stop the recording.
Oh, yes. Okay, I'm sorry.